109 and 77. 73. Okay. Hello. Hello. Looks like it's Dr. Shawana is hand. Hello, Hiro. Can you hear me? Hiro, can you hear me?
I can hear you now.
Okay, that's good. Okay, yeah. Probably let's start. Good afternoon, everyone. Actually, good morning there. So in Hobart time here is afternoon already.
Yeah.
So good morning, everyone. Welcome to this session 3. So today we will have 1 keynote speaker and 5 normal presenters in this session. So first, let's welcome Professor Nagai, who will give a keynote speaker on laser technology for on-site laser drilling of concrete. So Professor Nagy, it's all yours now.
Thank you very much for introduce. It's a great honor to be able to speak you today. Before I start, I would like to thank Professor Dr. Somnath Chatpat, this is Professor Dr. Firoz Alam, for inviting me to speak today. I want to share. Okay. Okay. Can you?
Yes, I can see that. Yeah.
Okay. Okay. Okay, here is the outline. Sorry, possible. It's better to. Okay, here is the outline of my presentation. Before start, I would like to speak about my background and then research background and surgery and method and the result and the conclusions. This is introduce myself from the Japan Nihon University and my PhD thesis, development of method of finishing building material using a laser. And I am an architect of the first class. This is the principle of my research. Keyword is durability, sustainability, and development. My main research is the durability of construction material. And then material development and the construction method development with laser. Target material include wood, concrete, stone, paint, and plastering, for instance. The target building are skyscrapers and historic.
Professor Nega, sounds like you are mute.
Oh, sorry.
Yeah, okay. Now it's okay, yeah.
Okay. This today's topic is laser application. This is my research with laser, and today's research is to drill the concrete. Already I tried the surface treatment and drilling, cleaning, cutting and microprocessing with high-power laser. So, let me start with some background information. The number of renovation works in Japan is increasing year by year, and it's beginning to exceed the number of new construction starts. For example, this is my field, skyscraper. This graph is stock of skyscrapers and large-scale repair work prediction. You can understand that repair work, renovation work is increasing. This is this area. Renovation work, the owner of the building often use it while performing the work, so noise, vibration, and dust are major problems. In addition, tiles are often used on the exterior walls of buildings, and fatal accident can occur when tiles peel off. As explained earlier, such construction has problems of noise and vibration that during work on the exterior wall performed by the gondola has a reaction force. Like this is me, which may be dangerous to the operator. Against this background, I am conducting development research focused on the low noise, low vibration, and no reaction force of laser. Until now, cutting and drilling have been performed using the high-power lasers such as until 10 kilowatt. But in this research, we challenged how much drilling can be done with the smallest possible laser power on the premise that the laser can be carried to the construction site. We conducted an experiment to test the capability of these smaller lasers. The targets for this research were diameter is 11 millimeter and depth is 30 millimeter. These are the most common conditions when repairing work. Now I will explain the specific contents of the experiment. The concrete used this experiment had compressive strengths of 20 newtons per square millimeter and 130 newton per square millimeter. The photo, this photo, shows a concrete test piece 20, 35, 50, and 100 and 130 newton from the left. The difference in density will also be the difference in the color of the test piece, as you can see here. 20 newton is used for general buildings, and 130 newton is used for skyscrapers. High-strength concrete is not used for the exterior material, but considering future applications, high-strength concrete was used for comparison in this experiment. This is a situation of laser drilling test. The laser used is a 500 watt fiber laser. Assuming a wall, it irradiations parallel to the wall, like this. Since the target depth of the experiment is 30 millimeters, the concrete specimen was set to 50 millimeter thickness. This is the condition of laser for testing. The laser conditions were tested by changing the frequency and irradiation time based on the result of the preliminary test. Next is evaluation method, measurement of the drilling diameter and depth, and observing the surface and cross-section in this paper. Next is the result. First, this graph shows how the drilling diameter of a drill changes depending on the laser conditions. The left side is 20 Newton, and the right side is 130 Newton. The X-ray shows the irradiation time, and the time increases as it goes to the right. The y-axis indicates the diameter of the hole, which increases as it goes up. This circle indicates 10 Hertz. The diamond indicates 38 Hertz. And the square indicates 60 Hertz. Within these conditions, the result of 20 Newton is in the range of 8 millimeter to 11 millimeter, almost this area. And it exceeds this condition within 19 seconds, just this, using a 38 Hertz. On other hand, 130 Newton shows a diameter larger than 20 Newton as a whole. And it was confirmed that some conditions exceed the target, this area. Next graph, I will explain the drilling depths. Left side is 20 Newton and the right side is 130 Newtons graph. At 20 Newton, the longer the irradiation time, the deeper the perforation depth is proportionally. In this test, the target value of over 30 millimeters was achieved under two conditions, like this. In the case of 130 Newtons, this right side graph, the perforation depth was not so deep, even if the irradiation time was long, this area. And the maximum depth was about just 17 millimeters, like this. Neither concrete was affected by frequency. That these three frequency is almost the same time. The next, the relationship between the drilling diameter and the drilling depth. This graph indicates to be impossible exceed to the target in this laser condition. This area achievement range. even though some conditions exceed each target. Each target meaning this is the diameter and during depths. It was found that is need to modify a little the laser irradiation condition. This means that it needs a more longer time irradiation. Next graph, influence of concrete strengths. It was found the correlation between the two intensities. This is a x-axis is 20 Newton and y-axis is 130 Newton. In the left side is diameter graph and the right side is during depths. Look at the graph. The influence of the diameter is earlier. That is, the surface part does not differ due to the difference in strengths in almost the same. Diameter can be obtained. On the other hand, in the case of during depths in this graph, there is a correlation at the depth of 15 millimeters. This is area. But beyond that, the depths tend to become shallower at the boundary of 25 millimeters, like this. It can be seen that the during depths is clearly shallower after 19 seconds. To find out the cause of this, the situation of the laser during a cross-section photograph of a test piece obtained by laser drilling high-strength concrete is shown. This is a 130 Newton concrete test piece with the same frequency but different time. Left side is 20 seconds. Right side is 19 seconds. You can see that the perforation depth is deeper in 19 seconds compared to 60 seconds, this area. But the vitrification color of the surface, this area, of the surface part is darker. This indicates that the concrete component silica has melted and vitrification is progressing. In other words, it shows the energy is being used to form the glass. From the above results, I made a model showing the heat effect. The left side is 20 Newton, and the right side is 130 Newton. 20 Newton has a low density, and when it is irradiated with a laser, energy is transmitted and it can be durable, like this. On the other hand, in the case of 130 Newton, the density is high, which is quite dense. From the experimental result, it was found that in the case of high-strength concrete, the thermal energy for processing does not penetrate the surface, but spreads horizontally to form glass. Okay, finally is conclusion. The main finding of this study are as follows. Firstly, the frequency posed the minimum impact, whereas the irradiation period exerted a large impact on the concrete strength within the scope of the present experiment conditions. Second, the drilling diameter was almost identical even when the laser irradiation period was increased for the general concrete sample. The drilling depths could be increased by increasing the irradiation period, and an irradiation period of over 120 seconds is probably required to achieve the target drilling conditions. Third, laser drilling on high-strength concrete at an irradiation period of 120 seconds resulted in drilling diameters and depths of around 12 and 15 millimeters, respectively. What do these results tell us about? It's able to drill the general concrete with a 500-watt fiber laser if it sets over 120 sec. This is an important point. And then please look at this picture again. I started this research with this image more than 10 years ago. Until now, it was not possible to carry it because the size of the laser processing machine was large. However, the size of the 500-watt laser oscillator is now as small as fit on a gondola. So you can see that this image is becoming a reality. It's not in the future. We believe that quiet renovation work can be achieved. It concluded my presentation. Thank you.
Thank you, Professor Nagy. Thank you for your very nice presentation. So now it's time for questions. So any question from audience? So you just raise your hand if you have a question, or you just speak in case we do not see you. I raise hand. Any questions? All right, if you guys have no question, I have one question here.
Yeah.
For Professor Nagy. Yeah. So thank you. So first, thank you very much for your nice presentation and very interesting research work. I have one question. Have you compared the whole structure between the laser drilling and the conventional drilling technology? Because when I see you drilling the hole, they got a thermal expansion, right? A little bit of thermal impact. So this thermal impact may affect the hole strength and the shear stress around the hole in the concrete. So in comparison to the conventional drilling technology, so how this impact is? Whether this laser drilling will cause decrease of strength or increase the tension or shear stress around the hole?
Thank you very much for your question. Maybe this is, of course, right now, it's a very good situation for the no noise, low noise, and the low vibration, no reaction force, and no dust. But you said is yes, exactly. Laser is a very expensive. So that is a problem. And of course, I have to research more, checking for vitrification or something like this. But I can catch its possibility to bring the laser machine on the gondola because already some work for the architecture field, the construction field, we bring the laser machine to a construction site. So like this.
So what I mean is whether the thermal effect will affect the quality of the hull or not.
Yes, quality for, I already checked in the hull,
Yeah.
in the include the glass and inside the pin and
Yeah.
checking the strengths, tense strengths, but no problem at that time.
Okay. So the only issue currently, I think, is the cost and and also the size of the laser machine. It will not allow you to use it in a real size, in particular in the tall buildings, right?
Yes,
okay.
You're right.
Thank you very much. So any other questions? Any questions from our audience? It's a good time to learn. We still got a few more minutes. All right, if there's no questions, so now let's thank you, Professor Nagy, for giving us this interesting presentation. Thank you.
Thank you. Thank you very much.
All right, so Dr. Shivana, so do you want to share the second one? Okay.
Yes, so the next presentation will be from Mr. Thinakit Naruthanan from Metro University, Thailand. He will come for the topic of energy efficiency analysis of biochar production systems. Thinakit, are you ready?
Hello. My presentation is pre-record.
Hello, good morning all. I think Dr. Harun has asked to play a recorded video of Keynote. And is it all right to play the video now?
Yes, why not?
Yes.
Just play the, hold on, just share the screen.
Today, I would like to present my project, energy efficiency and economic analysis of biochar production system. Biomass is an economic substance that is natural energy storage and can be used to produce energy. Agricultural waste has been developed as an alternative energy source instead of fossil energy sources such as oil, gas, etc. Production of biochar by pyrolysis is the thermal conversion of biomass in high or efficient conditions. In biomass pyrolysis, solids, liquid, and gases are produced. Biochar is the final product of agricultural waste pyrolysis. Biochar production technology could reduce environmental impact as caused the greenhouse effect of environmental pollution. In the biochar production process, peroxide and feed gas are released into the environment. Much energy is wasted. Therefore, the use of waste heat is a solution in the biochar production process as a source of high temperature effective heat recovery can be realized by a heat exchanger. In this work, energy analysis of the biochar production system with heat recovery was undertaken. Materials, corncob, rice husk, and mountain husk were used in this work. Initial biomass moisture content was determined by measuring the initial and final weight of biomass sample placed in a hot air oven at 100 degrees Celsius for 24 hours. The biochar production system was divided into two parts by 200 liters biochar tins and a labeling tin. The work process was to produce biochar from the 5 tins. The fuel gas containing smoke from the process was forced into the labeling tin and the smoke collector. Furthermore, the waste heat from the fuel gas was recovered and transferred to the working fleet through a coil heat exchanger inside the labeling tin. Biochar use. Average biochar use, the temperature was controlled to be always above 300 degrees Celsius. It was found that the biochar used from corncob, rice husk, and mountain husk were high. Use are 60%, 59%, and 64%, respectively. And energy of the biomass is purple, and energy of biochar is pink. When biomass is converted to biochar, the energy of the materials increases as shown. When analyze energy balance, it can divide T plus for average inlet energy. Energy from biomass of biochar tins, energy from fuel feed biochar tin, and energy from the fuel feed of labeling tin. First, for corncob, 45.7%, 22.6%, and 31.7% respectively. Next, rice husk, 38%, and 36.2%, and 25.8% respectively. And the last for inlet energy, mountain husk, 46.2%, 22.4%, and 31.4% respectively. For average energy will also divided like with average inlet energy. Biochar water heat exchange energy loss. First, corncob, 47.7%, 2.1%, and 50.2% respectively. Next, rice husk, 28.9%, and 2.6% and 68.5% respectively. And the last for outlet energy, long-term has 44.9% and 2.1% and 53% respectively. From the foregoing, it was found that energy of biochar varies because the property of each biomass are different. So when analyzing the efficiency of system, it was found that compost is 50%, rice husk 32%, and logging husk is 47%. When analyzing the economic, it was found that payback period of corn crop, rice husk, and logging husk are 8.2, 9.3, and 8 months. So the base efficiency system in this work, the base biomass for high efficiency of system is corn crop, about 49.7 plus minus 0.9%, and the base of payback period is logging us about 8 months. This my reference. Thank you for your attention.
Any question from the floor, please?
Okay, probably I ask one question. All right. So I see you presented the economic analysis, and you discussed the payback period. I think the sum of the one is about 7.5 months or 10 months. So for this payback period, so what kind of the capital cost was involved? Can you give us a little bit more explanation about how you conducted this economic analysis?
Sorry, you can you speak slowly?
Oh, okay, sorry about that. So my question
Thank
here is, could you please explain a little bit more about how you conduct the economic analysis for payback period?
I calculate from revenue and cost. Okay. Okay. For the material, the best material, I calculate the payback period from the cost of 275,280 baht per year, and the revenue from selling a biochar was 1 million baht per year. It's for calculation is the payback period is the base ประมาณเนี้ยครับ Thank you.
All right, I think probably the connection may not be very good. I cannot hear very clearly. Sorry for that. I know. Yeah. Yeah.
But may I have one question, please? So the graph that you show about the months of each type of biomass, so how is related to the payback period or the economics analysis from your results?
Again, please.
In your slides, you have shown the graph that talking about the months of the long gang, the month of the corn crop something. But you didn't show the methodology. So can you explain the relative between that month with your economics analysis, please?
I don't.
That is the lifetime of the crop or something.
Oh. I don't put data for economic analysis to methodology in presentation, but in my paper it have
That's fine ครับไม่เป็นไรครับ I will continue with your paper for if I have any question I will contact with the responsible author. Thank you. Any more questions from the floor, sir? So shall we continue to the next ones? So thank you ครับขอบคุณครับ the next presentation will be presented by Dr. Thanasit Wong Siri Amnoi from Major University, Thailand, in the topic of production and the characterizations of fuels briquette from lighthouse and tobacco stock.
Good morning, ladies and gentlemen. I am Thanasit Wong Siri Amnoi from Major University. Today, I would like to present my research. The title of production and characterization of fuel briquette from rice and tobacco stock. There is a rising interest in an alternative renewable energy source. Biomass is the most promising of this sustainable energy source because of its worldwide availability and renewability. Agricultural biomass, particularly agricultural residue, has grown in importance as one of the most extensive utilized renewable resource, and they have contributed to reducing the cost and enhancement the long-term sustainability. The typical of increased density may increase transportation, cost management, and storage since it requires smaller volume, make it more compact and easier to use. Briquette from agricultural residue were of interest and used for residential and industrial heating, including application in many industries. There are three primary techniques for increasing density: high and medium pressure with heating and low pressure using a binder. Various techniques were used to enhance the quality of well liquid, including mixing and varying the biomass ratio. Biomass density was affected by the material property and compaction conditions such as temperature, pressure, dye angle, size, and humidity. The higher temperature and pressure used could increase density of the fuel liquid. Most previous studies found that durability decrease will be effect on particle and operation transportation. Low compaction pressure and less overconsumption can be achieved by using a high dye temperature. Increase the moisture content could increase the strength and density until they reach a maximum. Many researchers study on rice husk liquid production, such as the effect of material, moisture content, mixing ratio, and process condition on property of liquid production. Topical residues stop and leaf were burned on farm in opening area. They generate air pollution and carbon dioxide. Converting this residue to renewable energy could be useful, but there are young research study on densification. Mixing of rice husk and with tobacco liquid also have not been yet studied for their characteristic and property. The objective of this research will study on liquid production and liquid characteristic. Biomass material such as rice husk and tobacco stalk in this research use Bury and Virginia. We collect from Chiang area. The moisture content of this material will reduce to less than 10%. Tobacco stems were also mixed with rice husk as a mass ratio of 20 and 80 by weight. A screw extruder was used for liquid production, coupled with an electric motor with a capacity of 25 horsepower and a speed of 970 RPM was used. 3 electric heaters were used as a heating source and a dye. 3 range of temperature was used in the length of 300 to 390 degrees Celsius. Physical property of liquid were determined following as density, compressive strength, water resistance capacity, and durability. Density was determined using the weight ratio per volume of liquid. The liquid density was measured immediately after from a dye, and lilac density was measured after 30 minutes to 7 days. A durability test was done by according to the standard by using a tuber at a speed of 21 RPM for 5 minutes. 2 kilograms of liquid were placed in each test and 3 replications. The liquid left on the seat was calculated for durability from equation 1. Compressive strength was calculated following the ASTM as equation 2. Force max was the maximum force that was used in kilogram, and A is the area of the compression area in the case. The water resistance capability of the liquid was determined by the submerged liquid in a container filled with the water, where M is the mass of the liquid and M1 is the initial weight before immersion, and M2 was the final weight after immersion. Then the water resistance capacity was calculated following the equation 3. Result and discussion. Density is shown in figure 2. When the dye temperature increased from 300 to 390 degrees Celsius, the instant density of the liquid decreased around 40 to 50 kilograms per centimeter, from 833 to 720 for rice husk, and from 900 20 to 800 to 70 for mixed biomass. Mixing of tobacco stock could increase the intensity of the briquette compared with the rice husk briquette by around 5 to 11% and 16 to 20% at 300 and 360 degrees Celsius, respectively. The reactancy after keeping the briquette for 30 minutes to 7 days, the briquette made from rice husk and mixed biomass remains similar in density. Increasing the temperature over 300 degrees C in the die could help decrease the friction and compression. It could also soften the binder within the material and help briquettes solidify better. If we use the temperature higher than 390 degrees, the compaction pressure is deficient and the briquette cannot be compaction. The moisture was important when water-soluble compounds were present in the feed, such as starch and sugar. Also involves stability and expansion after compression of the briquette. Also, lignin binder was shown to help the bridge microgap between the boil particle. High pressure also generate high temperature in the die, melting the binding agent and increasing the briquette compaction and density. Next is the durability. As shown in the figure 3, the durability also increases similar at the density when we increase the temperature, and the durability of briquettes was between 50 to 99%. And durability of the rice husk briquette was higher than 90%. But when it's mixed with the tobacco stock, it was lower than 90%. When the die temperature was higher than 330 degrees C, the durability of the mixing briquette decreased because the tobacco has lower lignin content, less than 1%, and higher fat and protein than rice husk. At the same time, lignin and starch could form bridges and film matrix or cause chemical reaction to form a solid interparticle bond, resulting in high durability. Feedstock moisture content improve the intermolecular and interfacial interaction. The biparticle together by pressure and temperature produced by the die when we use the high temperature. The strength and durability of the densified briquette could depend on the physical force that bind the particles together. When we use the high temperature, it decreases the compaction force. It decreases the friction force between the die and the briquette. Durability of the mixed biomass was higher than 90% at the temperature of 300, giving a high quality of the briquette. The compression strength as shown in the figure 4, the resistance of the briquette was between 0.3 to 1.1, increasing the die temperature, resulting in a decrease in briquette strength. Compression of the briquette decreased when mixed biomass was used compared to rice husk. High compaction resistance results from high compression force, making the particles close together. The compressive strength of sample could be affected by material properties such as particle size, moisture content, and porosity. The water resistance, as shown in figure 5, it was between 60 to 83%. It decreased when we increase the temperature, similar to those physical property. And when we mix the rice husk with the tobacco stock, it also decreased. Water resistance capacity of the Virginia were lower than the barley. Particle size of tobacco residue were bigger than rice husk. This increasing size of material resulting in decreasing water resistance. Also, a decrease in compaction pressure results in decreased water resistance due to the sealing up of smaller void between particles prevents water from infiltration and passing through it. Conclusion: the liquid density, durability, compressive strength, and water resistance capacity was found to decrease when increasing dye temperature and when mixing the topical stock with the dry husk. And the temperature that is a suitable condition for making liquid that we can receive high durability index more than 90%, compressive strength more than 2, and water resistant capacity more than 50% is a temperature around 300 to 330 degrees Celsius. Acknowledgement: this research was supported by the research and researcher for industrial and Metro University Graduate School Scholarship. Thank you for your attention.
Thank you ครับ Dr. Thanasit. So any question from the floor, please?
Okay, if no one asks, I'll start to ask. It sounds like I'm here to be responsible for asking questions. All right, I think this is a really good presentation. Thank you very much, Sir Nasit. I think the presentation is very clear to me, but I just have a couple of questions. So first, when you studied the density of the material, have you considered the packing methodology? Because different packing, I think the density of your material will be different, right? So how does a packing structure will affect the density of the material?
We control the die size. We can measure the shape and the diameter and the length of the liquid, and we can measure the weight of the liquid. Then we get the mass and the volume of the liquid. We can calculate the density. We have two density that we measure. One is the immediately that come out from the die, and the relaxed density we measure from 30 minutes after from the die to 7 days.
Oh, okay. So basically, is the density you measured is based on your current packing structure?
Yes.
Okay,
we have the fixed shape of the liquid.
Yeah. Okay. So another question here, my question is, you studied the density, you studied some other parameters. So how about the energy density? This is more important to me. So what is the energy density?
Energy density, we already calculated, but we not include in this paper. Yeah, we will write it in the extend paper. Then the energy that we use for making the liquid is around 30% of the liquid energy that we take it to put it to make it compaction.
I see. So when you conduct or you how to say calculated the energy density, so do you consider the energy you use to remove the water? Because
we control the moisture content. Then the biomass normally we decreasing the moisture lower than 10% before we compaction. Yeah.
All right. Great. Thank you.
Okay, I think it's time to move to the next presentation. So next, thank you, Mr. Thanasit. ขอบคุณครับ Next, we have the video from Mr. Thanakit Limkam from Metro University, Thailand, in the topic of heavy metal adoption by biochar made from longan seed and peels.
Yes, sir. I'll be sharing the video.
Thank you. Thank you, Biwan.
Yeah, it's the video.
My name is Sanakit Intam. Today I will present you heavy metal absorption by biochar made from long gum seed and peel. Let's start in introduction. Biochar is a product from agricultural or waste or organic waste via slow pyrolysis at the proper atmosphere and temperature. It can be mixed with the soil to improve cultivation. The heavy metals such as arsenic, cadmium, or lead are dangerous chemicals. They are generally contaminated in the soil from industry or remaining facility. Soil in the residue or agricultural area are contaminated with heavy metal will be devisely affect to the health of those who receive it to accumulate in the body. This study aims to study the capacity heavy metal absorption by the biochar derived from long-term residue. Material and method. The real material is a long-term residue from seed and peel. Both material were subject to pyrolysis at 300 Celsius for 4 hours with a heat rate of 5 Celsius per minute and dry it in a hot air oven at 105 Celsius for 24 hours and get it to determine pH and EC. The heavy metal are solution of single black fertilizer mixed with DI water. In the absorption experiment, we used 0.4 gram of biochar was mixed with 100 ml of heavy metal solution. The solution was checked at a speed of 200 rpm for 0.51246 12 and 24 hours and was filtered. The concentration of arsenic and lead was determined by ICEP. And result and discussion. The table 1 shows the VLP appeared to contact more green mineral than the VLS. In addition, the pH and EC value of the VLS were 7.92 and 344.57 micron, respectively, which were smaller than those of the VLP. Arsenic and grease contained in the fertilizer before mixing with DI water has concentration of 26.33 ± 5 ppm and 9 ± 5 ppm, respectively. After mixing, the solution was test of the track element with SIF. So the concentration of arsenic and lead were 16.83 ± 3.5 ppm and 5.92 ± 4.33 ppm, respectively. In a composition of track element, detect in a VLP before and after check in a figure 2I. VLP had additional element of titanium, iron, arsenic, rubidium, sodium, and lead. The highest element is iron, which had a concentration of 5,993.96 plus minus 122.68 ppm. And composition of tech element detected in a BLS before and after shake. In a figure 3I, the compound is in a BLS after shake was titanium, iron, arsenic, sodium, and lead. And the highest element is iron, which had a concentration of 2,120 plus minus 18.75 pm. And the surface of the biochar was predominantly negatively ionized with the ASEP positively ionized element such as iron, cadmium, or titanium. The biochar absorbent solution or element until structure and don't able to absorb element equally. In a figure 4a, show a arsenic contact after shake at 0.5 to 24 hours, and in a figure 4b, show a lead contact after shake shaking to 0.5 to 24 hours. In the figure 5a, show arsenic contact after shaking at 0.5 to 24 hours, and in figure 5b, show the lead contact after shaking at 0.5 to 24 hours. Arsenic and lead dependent on the number of the check element. When detective biochar electron bound to the element another than arsenic and lead, it could have a low number for negative electron on the surface in the biochar, resulting in the higher almost of the arsenic and lead, less water capture and different time. Conclusion: in these experiments, the biochar derived from Longkong peel and Longkong seeds was tested for the absorption of the arsenic and lead. The BLP was for absorb more arsenic and lead than the BLS. The BLP can absorb significant almost of arsenic was 14.33 plus minus 3 ppm at shaking time of 0.5 to 2 hours, and 6.8 plus minus 4.23 ppm at 4 to 24 hours. While the BLS absorbent a smaller most of arsenic was 4.78 plus minus 3.56 ppm. The lead absorption of the BPL at the shaking time of 0.5 to 24 hours was 4.48 plus minus 3.27 ppm. Washed with higher than the BLS was 1.63 plus minus 1.25 ppm for the same period. And thank you for watching.
Thank you, Mr. Thanakit and also Mr. Bavin for the video presentation. Do you have any questions? Actually, I have one question that I'm not clear from the presentation. And what is the benefit for study of of absorbing this method? I mean, after we know how much the heavy metal absorbed by the biochar of these two longan seed and peels, what is the application of this one that you plan to use?
Again, with
The question, the question is, tell us a little bit about the application of your technology.
or is a benefit, right?
Yeah, where it can be used. Yeah.
When we know about how many long kong peel and long kong seed can absorb heavy metal, and we can use to use long kong peel to absorb arsenic. Yeah, so we don't use long kong seed to absorb arsenic because biochar long kong peel can absorb arsenic more than long kong seed. Yeah.
Yeah, we know, but where you can use? Where? In what situation? Yeah, where? Is just, for example, is somewhere they got a lot of these heavy metals. So you use this kind of plant there and use this plant to absorb the heavy metal from the land, or what other applications? So this is the where you can use it.
Oh, first we must take soil or soils to scan for arsenic. If in the soil have arsenic more than 5 ppm or more than law in have arsenic, yes, we can use biochar to absorb this for decrease value of arsenic in the soil.
All right, I think it's time. So we probably move to the next presentation. All right, so our next presenter is Mr. Paraja Pillai from Kasetsart University, Thailand. So his research title is Hard Carbon Production from Corn cob and Oil Palm Empty Fruit Bench for Anode Material in Lithium-ion Battery, a comparative study of hydrogen carbonization and carbonization. All right, so Mr. Pillai, it's yours.
Yeah.
So you can start to share the screen. Yeah.
Can see the sharing.
Yes, we can. Yeah.
Yes.
Good morning, everyone. I'm Panjapali, student master degree from Kasetsart University. So today I'm here to present my work about the hard carbon production from corn cob and oil palm empty fruit bench for anode material in lithium-ion battery. Okay. Let's begin. Okay, outline today is introduction, material, method, result, and conclusion. Okay. In past few years, many equipment battery usually made by lithium-ion battery, example, telephone battery, camera, medical, portable device, and even in the medical equipment. According to the short graph, indicate the demand and usage of lithium-ion battery significant increase in every year. In my point, I try to make this battery for biomass waste to reduce the cost from lithium-ion battery industry. So let's take to look next section. The component of lithium battery was made in 3 electronics: anode, electrolyte, cathode. So we focus on hard carbon that's able to make an anode charge lithium-ion. On theory that either carbon can keep the lithium charge. Okay. In my study, I select the corn cob and empty fruit bank to represent to high percent humidity biomass as a raw material to proceed the hard carbon in pretreatment and go to the hard carbon. I will discuss in next session. Okay. The method. I would like to tell about pre-treatment to process and put the two raw material to pre-treatment process, hydrothermal carbonization and carbonization to get the char, and then put those in the activation process to get the hard carbon and increase the surface and high porous. After all, I will put it in the hard carbon to use the anode in battery. Okay. The hydrothermal carbonization, I will use the high pressure autoclave with the temperature to 220 degrees Celsius and holding for 2 hours. And after that, I will separate that and drying and get to the finally the hydrochar was getting. The carbonization. The carbonizer was used in synthesis. The temperature of carbonization was 300 and holding 2 hours. And washing with DI and drying. And finally, I will get a product, Biochar. The chemical activation, I will use the tube furnace for product, for produce this. The char product will impregnate with the KOH and put them in tube furnace and heat up to 200 and holding time 1 hour and go to 800 Celsius and holding time 1 hour and clean it for natural with HCl and washing it and drying, and final I will get a hard product, hard carbon product. Okay, I will talk the result. The picture is present the product from process. And table, it shows the yield product from each the process. According to the table indicate that the composition of mass is pre-treatment process product chart left amount of 35% by weight. And other hand, after activation process, we slightly decrease to 10% by weight. At the table, it shows the pore texture of hard carbon. Indicate that the average pore diameter value in every process is currently in 1.7 nanometer, and BT surface area approximately 1,000 square meter per gram. However, the hard carbon from hydrothermal process is little less in BT surface area and hard carbon product from carbonization process. The graph is show chart discharge capacity in battery. Indicate that all process perform similar graph when compared with the conventional lithium-ion battery, and that anode charge and was made graphite. The hydrothermal carbonization carbon was the perform the peak in capacitor more than carbonization carbon. Besides after the 30 cycle, the hydrothermal carbon still perform high peak when compared with the conventional lithium-ion battery. However, in my future study, I will investigate that why hard carbon product of the hydrothermal carbonization carbon perform high peak. Okay. The conclusion: the hard carbon were prepared successfully via official and low-cost method, and after activation, material were changed on microstructure, and the hard carbon electrode deliver good capacitance and lead capacitability. And the product yield of hard carbon using the hydrothermal carbonization process was higher than the carbonization process. Yes, thank you very much.
Thank you for your presentation. So now it's a time for question. So any question from audience? Any question from audience? All right, if no question from audience, can I have one question? Could you please go back to your third slide from the end regarding the test results?
Right.
The third slide from the back, from the end. You did a 50 cycles test, and we see the peak value of the, yeah. Can we share your screen? All right, so my question actually is regarding the values you obtained from your 50 cycle test. And yes, just go back. Yeah, this one, yes. No, the previous one. The previous one.
Previous.
Yeah, go down. Yeah, that's right, this one, yeah. So for this one here, I can see that, just give me a minute, it's the end note. So for this one here, basically it almost reached the stable situation after certain cycles. But this one here continuously drop. This one here also continuously drop, haven't reached the stable situations. So for this kind of experiment, do you need to continue to have more cycles until this one reach the stable condition? Then you will conclude to say, okay, so what is the capacity of this battery? That probably the results will be more accurate, right?
Right. I think then the next work I will get the long cycle more.
Yeah, because I think you need to reach the stable condition. Then you know, okay, so this battery has a good capacity or has a low capacity, has a high capacity, right? Otherwise, for this one, continue dropping after 100 cycles maybe drop to 0, you do not know. But this one here already in a stable situation, sounds like it, right? But this one also almost similar to the stable situation looks like, right? Yeah, I think you probably need to have more cycles to see how many after how many cycles this specific capacity will reach the stable values. So that will provide you some information about which combinations here is better. Is that right?
Right.
Yeah. Okay. Thank you. Any other questions? Any other questions? All right. If you have no questions, so now let's move to our last presenter. So our last presenter is Mr. Gautam Natarajan from the ABC Cube Engineering and Education Service Company, Australia. So his research title is Modeling Air Distribution Inside a Shipping Container Size Plant Factory using Computational Fluid Dynamics Case Study. So Mr. Natarajan, so all yours now.
Thank you, Dr. Wang. Good morning or afternoon to everyone around the world. I'm Gautam Natarajan from ASEP Engineering and Education, here to present our study on modeling air distribution inside a shipping container size plant factory using computational fluid dynamics. The main objective of our study is to analyze the distribution inside a shipping container, that is the airflow distribution and temperature flow distribution with different inlet and exhaust location. Computational fluid dynamics plays an important role in designing and analyzing the schematic design of the indoor environment by analyzing the uniformity of the flow distribution and how effectively it contributes to the growing conditions for any plant that is grown in that environment. I would say that considering lettuce as the plant for our study, we took forward to analyze the literature review for evaluating certain important characteristics such as the optimum workable temperature to be around like 15 to 27 degrees Celsius and the airflow to be around like 0.2 to 0.3 meter per second for any leafy vegetables on near the surface. But when the airflow is below 0.28, there is a decrease in the transpiration rate, which increases the tip burn effect. Which is not really an ideal case for any lettuce plant. So this is where we understood what are the important characteristics and the values through our literature review. Analyzing all these, we concluded that three major configuration for our geometry, and the baseline configuration was modeled using a computational model as a shipping container with two inlet diffusers and an exhaust duct, where we had 4 sets of racks and an isolated rack, which you can see there's 4 sets of racks over here and an isolated rack. And the average height of a plant to be around like 0.10 meter, which was found from literature review, has been modeled as a rectangular prism in this case. A separate user-defined function has been created to define the plant as a porous body so that the turbulence effects on the leaf surface are defined by certain aerodynamic assumptions, such as the coefficient of drag to be around 0.32 and the leaf area density to be around 0.251. So once the geometry has been modeled, we all know that the meshing is one of the important steps in the computational simulation. So the modeled domain is being discretized into 6 million polyhexahedral cells, and the inflation layers are applied to all walls to enable adequate boundary layer resolutions. So from this image, you could see that the slice showing that the mixed hexahedral and the polyhedral volume mesh and structured inflation layers are there to capture high near wall gradients. These are some of the simulation details and the boundary conditions that we have used in our energy model. The gravity minus 9.81 has been used over here so that the effect to indicate the effect of the buoyancy, and the energy equations are also activated. The simulation is a steady state, and Rand's K epsilon realizable turbulence model is being used over here. The important boundary condition is the volumetric flow rate to be around 0.38 meter cube per second, which is being supplied at a temperature of 18 degrees Celsius. So as we understood the simulation and boundary conditions, now analyzing the results plays an important role. As I stated earlier, computational fluid dynamics is a tool with which we could study the uniformity in the flow patterns inside the grow room. So first, let us understand the temperature distribution and how it affects the grow room conditions. The flow distribution were observed in two different planes in the ZX plane, one in the upper level, another one in the lower level, which you could see over here. And from this image, we could see that the upper level has slightly lower temperatures compared to the lower level, where from this over here, we could see that the temperature ranges from 19 to 20, around like 20 degrees Celsius. But whereas in the lower level, we could see higher temperatures near the isolated racks, or in most of the places, which is to be around like from 21 to 27 degrees Celsius. So from these two levels, we could understand that the temperatures are not evenly distributed inside the grow room, and the average temperature ranged between 0 to 12 degree above the supply air temperature. So this is due to the lack of flow supplies inside the grow room. So we could also see that there are temperature stratification between the walls, which are due to the lack of flow circulations at those points. To understand more about the temperature distribution, we could get from these images. In the isolated racks, as I stated earlier, we could see a higher temperature found on the lower level compared to the one on the upper levels. As the levels increases, we could see the decreases, the temperature has been increasing. And as I stated earlier, there's hot air due to LEDs are rising upwards towards the grow room ceiling and pushed towards the exhaust duct. This is generally a buoyance effect. And over here, we have a volume rendering showing temperature distribution inside the grow room or the whole shipping container. The flow recirculations are present inside the aisle of the grow room, which could be seen over here. But as I stated earlier, there are temperature stratification between the racks. We could also see there are temperature slightly higher on the eastern side between the aisles also. This is generally due to the reason of the flow recirculation. So now we understand that there is a relationship between the temperature distribution and the air circulation or the flow distribution. So understanding the flow distribution will give us a major way to go forward to have a certain grow conditions for the grow room. Let me explain you the velocity distribution in this case. As expected, there were lower velocities in the lower level because as the inlet diffusers are present in the upper level. In the upper level, the higher air velocities are set to penetrate deeper into the upper level racks compared to the lower level racks. But from this image, you could see that the lower level racks are having very low velocities. It's not zero, it is very low, such that it is not sufficient enough for the lower level lettuce plants to have effective growing conditions. So from this, we could recommend that there is a need for improvement for the lower level plants for an increase in extra supplies of airflow, or by adding extra inlet diffusers at these points. But as in the case of upper level, we could see that the air velocities are penetrating deeper into the racks, and there is a sufficient flow for the lettuce plants to have an effective grow rate over there. So from this, we could conclude that the computational fluid dynamics simulation are giving us a detailed analysis of the uniformity of flow inside the grow room, where the temperature distribution are not evenly distributed and there are insufficient air supply to the lower levels of the grow room. This leads to higher temperatures at the lower racks. So there has to be something to reduce this higher temperature. So in order to reduce these temperatures, we suggest that the conditions could be improved by increasing the flow supplies or adding multiple diffusers in different locations. So from this, we also want to give a future simulation configuration B and C for understanding how the grow room conditions would be in the future. So let me explain the configuration B and C that we are suggesting for future simulation. A configuration B with 4 inlets in the south facade with 1 exhaust as same as in the baseline configuration could be used. And while in the configuration C, which has 2 inlets in the south facade in the upper level and 2 inlets in the north facade in the lower level with 1 exhaust as same as the baseline configuration can be used over here. So the flow study from these two configuration B and C will help us to understand how in regard to how exactly the shipping container to be used as a plant factory will be effective for a society in having an increase in production of plants such as leafy vegetables, herbs, fruits, tomatoes, or anything in such regard. But in our case, we have studied lettuce, and analyzing these configuration will help us to know what will be the ideal grow room conditions for the lettuce. I would like to take this opportunity to thank my co-authors for their help and support during this research study and make this accomplished. I would also like to thank the organizing committee for giving me this opportunity to present our study in front of the chair members. I would like to take questions from the audience and the chair members so that I can clear any of the doubts. Thank you.
Thank you very much. So any questions from audience?
May I have one, please?
Yes, please. Yeah.
Mr. Gotham, can you go back to the model B and C again, please? The B
Yeah,
one,
sure.
I think. Have you planned to change the position of the exhaust?
We haven't planned to change the exhaust locations as of now, because as we have looked at the simulation results from our baseline configuration, we thought we will have inlet diffusers at different locations to understand the flow distribution in the first scenario. So with future simulations, we could, as we are in the initial stages, we are trying to figure out what are the best way in which we can go forward with the different configurations.
It's just some recommendation that I think the effect of velocity is come from the exhaust than the inlet, in my opinion.
Okay.
Thank you.
Thanks for that. Thanks for the suggestions. We will definitely look into it. Thank you.
I have one question here. I just want to ask for this cooling these vegetables. So normally it's preferred for laminar flow or turbulent flow. So which type of flow is preferred?
Turbulence flow is preferred actually. So the more turbulent the flow near the surface, it really helps the growing conditions for the plants in that surface. So that's why when I said we are trying to implement user-defined function for the plant for a porous body, we are trying to define the turbulence effects near the plant surface.
So then in this case, if the velocity is too high, it may have some damage on the vegetable surface, right?
So from our simulation, like the velocities in the upper level are around like 0.3 to 3.0 to 4.0. But from the literature reviews, it said that something about 1.0 is also optimum for the lettuce growing conditions. So the difference between 1.4 to 3.4 is not much, and it's not affecting. That is what we understood from the literature reviews or the experimental study that has been done by a few people in regard to this.
Yeah, the reason I ask this is because if you use the turbulent flow, definitely it will enhance the heat transfer. But at the same time, it may also enhance the mass transfer. So when it affects the mass transfer, so then the vegetables may lose the moisture inside inside the vegetables. It may affect the quality of the vegetable after it is stored for some time. You got my point, right? That's why I'm asking.
I understand.
Yeah, and I ask is normally is prefer laminar flow or turbulent flow, because I think it's kind of balance between heat transfer and the mass transfer. Is that correct?
Yeah, I understand, but I just have to look deep into it, but from our understanding, we had this kind of study going forward.
Do you consider mass transfer when you studied the airflow distribution in the in this situation?
No, we didn't.
You haven't, right? Okay, yeah. So this is
Yeah.
something I concerned because the mass transfers will affect the quality of your fruit or of your food or vegetables, right? Because if you lost a lot of water from vegetables, then it will have
We are
trouble.
not considering the mass transfer or thing
At the moment. Okay, yeah. Just a question. You probably need to think about this, yeah, in your future study, yeah.
Yes.
All right, thank you so much. It's a really nice presentation. If there's no any other questions, so we can close this session. It's really great to meet all of you here. Thank you so much for joining this conference, joining this session. So we hope that we could keep in touch for the future collaborations, for the future research works. All right, thank you all. Ms. Dr. Shawanat, do you have anything to say?
No, fine. Thank you very much. And of course, thank you our speaker, Professor Kaoli Nakai again.
Yeah. All right, thank you all.
Or we should take some photo together.
So that'd be good. So I think this I leave to Hero. Would you like to take some photos for all of us in this one here? Yeah. So I think you can take photos.
So everyone, would you mind turn on your camera, please?
Yeah. So can you open your camera, and I think we need to adjust it. The views. Yeah, I think we need to use gallery views. So Hero, I think we leave it to you for your taking photo now. You count 1, 2, 3. We will all laugh. Hero, you are mute.
Okay, thank you very much for your all your support and our presentation. Really appreciated, and see you in the next slide. So we have our next program, next session. So please feel free to feel free to join all those sessions. So
Hero,
thank you very much, and you also please join our other session, and also all of us also our keynote speaker. Thank you for your time, because you are so busy man, a busy lady, but I really appreciate your time, because you said that you are not doing some voluntary works on all those things. In between, you gave us your valuable time with your presentation, and all the presentation we are recording, and hopefully it will be also viewed by other people.
So Hero, can you take a picture for all these presenters?
Oh yeah,
here now?
That's good. Yes.
Yeah, that's what we suggested to do. You count 1, 2, 3, we all laugh, then you take picture.
All right. So thank you, everybody, and see you in the next what's called next presentation.
All right. Bye bye, everybody. Thank you. See you.
Thank you, Doctor. Mute.
Yeah,
mute. Oh, sorry, Doctor. Mute. Yeah. I think the next session is what?